All right, I'm going to give a shot to explaining what completing the square is, why we care about it, and how it works. So first of all, let's imagine that we have a kind of plain Jane parabola, quadratic, looks like this, of the form y equals ax squared plus bx plus c. You can see our a here is 1, our b is 0, and our c is 0. So right now this is plain old x squared. And this has kind of a familiar pattern. If you put in a 1, you get out a 1. If you put in a 2 for x, you get out a 4 for y. So we're squaring the input, right? And you can kind of see what happens when I change the a around, it changes the shape. We call it a stretch factor. When I change the b and the c around, it changes where the vertex is and kind of shifts it horizontally and vertically in the case of b, and just vertically in the case of c. But this isn't super intuitive. There's a way to figure out what's happening here. It's negative b over 2a will tell me the x value right here. I don't like that, though. I would like it if I could just find it in the equation, which we can do pretty easily using an equation of the form y equals x minus h squared plus k. You may have seen this before. This is vertex form of an equation. If we put our h and our k as 0, then our vertex is 0, 0. If we put our h as 1, then our vertex becomes 1, 0. Put our k as 3, our vertex becomes 1, 3. So in this format, your vertex is h, k. You could write this as a plus and just remember that your h is backwards because it's happening before all the inputs. A lot of people, I like to write it this way because then I don't confuse myself by getting double negatives in there, and then I just remember that the vertex is backwards. But in any case, this form is a lot easier to use for getting an intuition about where your graph is going to be and what it looks like, because you know exactly where your vertex is and you can calculate your scale factor pretty easily after that. So if a was 2, then all the values are just 2 times bigger. So I'll pull up a table real fast. All right, so I've made a quick table here, and you can see that when a is 1, the values in the table kind of follow a squared pattern. So negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9, and symmetrical on both sides. But when I make it times 2, we're just multiplying those values times 2. So it used to be 4 for this 2 value, but now it's going to be 8, right? And it used to be 9 for the input of 3. The output used to be 9, but now we're going to times by 2 and make it 18. So you can see with this vertex form, it's really, really easy to just take a normal parabola, x squared like this, and kind of watch where it goes as you shift it. If I move it over and I move it up, and then I scale times 2, I can do all those calculations pretty easily, kind of even in my head, without doing a whole lot of solving to find out where this sucker's going to land, right? So this is why vertex form is awesome. We love vertex form. But here's the thing, they give a standard form all the time because why? I don't know, they want to be irritating, I guess. Sometimes standard form is what you get. And there are actual standard form applications in physics, especially with position and velocity and acceleration and things like that. Those are some good applications. So standard form isn't totally worthless. It relates to the real world. But if I want to graph this sucker, then I want to look at it in vertex form. And the easiest way to get standard form to vertex form is by completing the square. So let's just take a look at an example real quick. So we have 2x squared plus 4x minus 7. Let's say that's our graph. Oops, we want y to be equal to that. And I want to turn this into vertex form. Put this question on hold for a moment. So we're going to kind of put this on hold, and we're going to come over here. Doop-a-doo. And we are going to talk about what I mean by complete the square. Let's imagine that I have a square, and I want you to really use your imagination here. I know it's not a perfect square, but we're going to pretend it is. And we're going to pretend that this is length x, and this is length x. Just so that we're super clear, if this was length 2 and this was length 2, this square would have an area of 2 times 2, right? You're multiplying the side lengths together to get the area. So if this is an x by x square, we're going to have an area of x squared. Now let's also imagine that we have another rectangle down here. And I want you to imagine it's exactly x long on this side, but it's a long on this side. And just so that we're super clear, same as for the square, for the rectangle, if this thing was 2 and this is 1, the area would be 2 times 1. We're multiplying the side lengths together, right? So if this is x and this is a, our area is going to be ax. So the total area, I'll write area here so it's clear, of this kind of square plus this rectangle is x squared plus ax. Right? You with me? Cool. Now I'm going to erase those things in the middle like magic. Poof, very magical. Okay, so what happens if we want to make this into a square? Well, I'm going to show you the easy way. We're going to take this rectangle right here, and we're going to cut it in half. Like this. Man, I'm going to redo this real quick so that's better and perfect. Hold on. Ta-da! Okay, now we're going to cut that rectangle in half. Boom. And this changes things a little bit because instead of this being a, we've cut it in half, right? So this is a over 2. That looks like a 9. I'm going to try that again. A over 2. If at first you don't succeed, try again, right? Even when your handwriting is crud. Okay, so these are both a over 2. I know it looks like a 9. Oh, good gravy. I just have 9 looking a's. We're going to go with that. And if we add a over 2 plus a over 2, that would be just 1a, right? So this is still the same thing. Okay, so after a wee bit of adjustment to ensure that I had a perfect square on the top, it wasn't actually square before. Now it is. I was just guessing, but now I'm not. We're going to take this bottom chunk right here, and we're going to flip it, whoop, kind of like that, and we're going to put it up here next to the square, and hope that I can kind of get that rectangle straight up and down. It's about as close as it gets. Cool. And now if we put a little tiny box right here, boom, or to be precise, a square right here, there's this little chunk that we're missing. And I'm going to color it different just so that we can see bright pink. This little chunk is missing, right? So far, what did we do? This expression didn't change, except there's a little pink chunk. Where's my pink? Right here, plus some chunk. We could call it like C, for example. We're missing this little chunk. So what is C though? We know the values because this is a over 2 and this is a over 2. So the C chunk is not just C, it's a over 2 squared. So let's write that. It's a over 2 squared. Cool. And it turns out that this thing factors perfectly every time. We know that it will because now this is a perfect square. See that perfect square shape? So here's the way that this factors. And this is really slick. I'll go back to my pink here. So what is this side length right here? This side. Well, it's x plus a over 2. We have an extra a over 2 just kind of hanging out for no reason. And all right, so this side of this square is x plus a over 2. And what's this side? Well, it's also x plus a over 2. A over 2. Cool. So this area is going to be x plus a over 2 squared for the whole square. This is why I use tools to draw squares, because I just can't. Right? So we know this is going to factor as x plus a over 2 squared. And now let's be clear about what exactly we just factored, because that's kind of important. The original part of this equation that we had in black was x squared plus ax. That was the original part, and we didn't add anything to that to get here. This pink thing, this plus a over 2 squared, is not part of the original equation. So we need to compensate for the fact that we added an extra pink square by subtracting it again. And what's the area of this square by itself? Well, the area of a square is the length times the width, right? Or the side squared. So let's just not 9, a over 2 squared. And this is now a complete the square. So we said that this thing is a over 2. I really should have called it b because we usually call this b in standard form. I could go back and change those all to b's, but I'm not going to do it. So shift in your brain that the a over 2 is actually a b. And so what we're going to do, same thing with this, is to complete the square. First of all, this pesky 2 makes this a little bit harder because if this is 2x and this is 2x, there's a scale factor and everything gets confusing. So how about we do the same exact equation first without that 2, just so I can show you what we're doing, and then we'll do it with the 2, so you know how to adjust when there's a number right here. Boop, that is not 1. Right now that's a 1x squared. So here we go. How do we do this? Well, we find our a over 2, and then we square it, just like we did over there. So or in this case, a b over 2. So b over 2 is 2, squared is 4. Cool. That's our square. That's our magic number right there. So we can just say this equation now is x squared plus 4x. And we're just going to randomly add a 4 here because now that's a perfect square. But because I added a 4, I also have to subtract a 4 or this equation is no longer true. So this thing right here is 0. I can add 0 to anything, right? It's cool. It doesn't change anything. I just put this magic 4 right here. And then we're going to subtract 7 as well, because that's part of the equation. We don't want the equation to change. I just kind of shoved this thing in here, which is a fancy version of plus 0. But here's the cool thing. Go do your factoring tricks on this sucker, and you'll find out that it always factors, if you did this right, as x plus b over 2, remember that? 2 squared. Where's that? Over here? X plus, I wrote it as a here, x plus a over 2 squared. If we multiply this out, we find that it equals this. Cool. So this thing is equal to the thing up here. But we still have the minus 4 and the minus 7 here, and we can put those together to get minus 11. Cool. Let's prove to ourselves that these are the same. This and this. So x squared plus 2 minus 11. Boom, graphed. And then let's also do the original, which was y equals x squared, not the original, the factored form. X plus 2 squared. What was it? X plus 2 squared minus 11. And this should be minus 7 because I'm a goofball. Ooh, did I write this wrong? Yes, there we go. X squared plus 2x, it's 4x. Man, I'm really bad at writing things. There we go. Oh my goodness. X squared plus 4x minus 7 is indeed the same thing as x squared plus 2 squared minus 11. If you write the equations the right way. Good gravy. This is why we double check the things we write. So they're the same. Cool. This is awesome. But what do we do when there's this pesky 2 in the way? Going all the way back to our first question, how do we do that? So I'm going to move this stuff out of the way, and we're going to do exactly the same thing, but first we're going to factor out a 2. So all I'm doing is I'm saying I can divide this whole thing by 2 if I also multiply this whole thing by 2. That's just times 1, right? It's a fancy version of times 1. So let's rewrite that. Like this. And I'm going to divide the whole dang thing by 2. This is pretty cool because it turns out we can actually distribute this 2 through this 1/2, if you want to look at it that way. And we get a new thing that gets rid of the 2 at the start. Cool. Not too bad. And now this thing, we can complete the square in the same exact fashion that we just did. We'll leave the 2 on the outside, and then we'll multiply it through, and we're done. Right? Nothing's changed. Just keep in mind, this is still equal, right? Because we just multiplied by 1. So what are we doing now? We're completing the square. How do we do that? Well, this is the a over 2 squared chunk that is missing to make this into a perfect square. So a over 2, or in this case, b over 2, 2 over 2. 2 over 2 squared is just 1. So the thing here that we need to make this a perfect square is a 1. Okay? Which means we're going to just add a 1 randomly. But to keep it balanced, we're also going to subtract a 1 inside. Is that okay? Yeah, because we just added 0. That's just 0. And then we still have minus 3.5. This thing, just as we said over here, is a perfect square and will factor as x plus a over 2 squared. So this now becomes, I'm going to take this thing that is a perfect square, I'm going to make it a perfect square. X plus a over 2 is 1 squared. And then we just write the things that are left up here. And you'll notice that this is minus a over 2. So minus 1 and minus 3.5. When you put all those together, minus 1 minus 3.5 is minus 4.5. There should be an equals here, I think. And you have your perfect square minus 4.5 that we then distribute the 2 through, and we are left with a lovely complete the square equation in vertex form, which is very usable. And to prove to ourselves that this is actually right, I'm going to go graph it. Boom. Is the same thing as this 2x squared plus 4x minus 7. So let's try that. 2x squared plus 4x minus 7. That's not a squared. There we go. And are they the same? Oh my goodness, they are the same. So here we have it in vertex form where we know immediately upon looking at this that our vertex is in fact at -1, -9. We also know that it has a stretch factor of 2, so I'm going to go over 1 and up 2. And then over 2, 1, 2. And instead of up 4, we're going to go up 8. Up 8. Right? Fun. That was 9. We don't want that one. That is 8. There we go. Cool. And it turns out, while we're on the subject, where are these roots? Well, it doesn't matter what multiplier you have in front here. So when you kind of factor it out in that complete the square thing, your roots are going to stay in exactly the same place, no matter what that multiplier is. So when we completed the square, it makes solving for these roots way easier. Let me show you. See, we want to find where this is 0, where the y is 0 on the x-axis here. So let's set our y equal to 0. And then we just solve by doing the order of operations backwards, right? So we have our -9, so we're going to add 9 to both sides. And then we have our times 2 is the multiplication, which happens before the exponent and when we're undoing it. So we're going to divide by 2 on both sides, which is 4.5. We've seen this number before today. And then we have our x plus 1 squared. Let's square root both sides. And when you square root a positive number, you could be getting the negative version. So you have a plus or minus. It could be positive. It could be negative. We don't know. It could be either of those. And then x plus 1. And we subtract the 1 from the inside. And so our result is plus or minus the square root of 4.5 minus 1. And that's 2 results. And those are these. To convince ourselves this is true, we're going to do a line at the square root of 4.5 minus 1. Oh my gosh, it's right where it's supposed to be. If we make it negative, it's right where it's supposed to be. Look at that. Isn't that sweet? So completing the square not only gives us the ability to graph things much more intuitively, it also helps us solve quadratics more intuitively without the need for the quadratic equation, which is amazing. So there you go. Hope that intuitive explanation of complete the square helps.